thing. Okay, so we apply inverse function theorem to phi. Phi is a map. Phi is a map from omega to Rn. So that phi a, maybe I will write here. Phi a is fa0. That is b0. Okay, fa is b. B is a point in Rm. B is fa in Rm. Okay, so apply the inverse function theorem to this map phi. There are an open set in Rn containing the point A. That is, the open set is n. In our family of open set containing A, this is our notation. And also another open set, also in Rn, containing the point B. So that phi from U to V is a diffeomorphism. Phi is locally a local diffeomorphism at the point A. So we have open sets containing A and containing another open set containing the image of A. That is B0. Sorry. So that phi is a bijection between these two open sets U and V, and the inverse map and the phi itself are all smooth. So this is diffeomorphism. Okay. So this is the conclusion of the inverse function theorem. Now, V is an open set containing B0. This is remarkable. B is open set containing B0. So B0 is an interior point of V. So because V is open, therefore we can take an epsilon positive such that the epsilon neighborhood of this point B0 in Rn, you should know that you should be careful that B is a point in Rm. Okay, and 0 is n minus m. Therefore, B0 is a point in Rn. So we have a epsilon neighborhood. This point is an interior point of V. Therefore, we have a small epsilon, so that the epsilon neighborhood of B0 is contained in V. But V is precisely phi U, and U is a subset of omega. U should be a subset of omega. So this is contained in phi omega. Okay. Now, from the definition of phi, we see that the same epsilon we have obtained an epsilon, so that the epsilon neighborhood of B0 in Rn is contained in phi omega. Now we claim that the epsilon neighborhood of B in Rm, because B is a point in Rm, right? B is a point in Rm. Look at the right upper corner. B is a point in Rm. So we claim that this is contained in F omega. This is what we want to prove. Once we prove this, this means that B is an interior point of F omega, and the proof is complete. Okay, so we prove this claim. How to prove this claim? We take Y from the left hand side, for y in the left hand side, then y0 minus b0, this is y minus b. Okay, this less than epsilon. This means that y0 is n minus m ordered 0 point. So y has m coordinate, 0 has n minus m coordinate. Altogether they have n coordinate. This belongs to b0, because the distance from y0 to b0 is less than epsilon. So this point belongs to the to this ball. But this ball is contained in phi omega. Okay, but remember our phi x is fx x m plus 1 minus a m plus 1 and so on. Okay, so the first m component of phi x is fx, but now the first m component of y, y0 is y. So we have to this means for some x in omega, y0 is fx xm plus 1 minus am plus 1 xn minus an. Okay, so comparing the first m coordinate of this equality, we see that y is fx. So y is fx, which is a point in f omega, because x is taken from omega. So this proves that our claim, any point in this ball, any point in the left hand side y, any point y in the left hand side contained in the right hand side. Okay, so this proves this claim. Therefore, B is an integral point of the image f of omega under our map f. So our theorem is proved. Okay, so our theorem the theorem we just proved says that if for the map for f defined in an open subset of Rn to another Euclidean space Rn and A in omega, if the length of is m, this means that the linearization is surjective. This means the derivative matrix as a linear map from Rn to Rm is surjective. Okay, under this condition, then fa, that is our B, is an integral point of f omega. Okay, so this is the theorem we just proved. Now, if for any x in omega, the rank of the derivative matrix at x is n, then from our theorem, fx is an integral point of f omega. Right? Applying the result to a equal to x, we get the latter conclusion here. But now, for any y in f omega, y must be some fx for y must be fx for some x in omega. Okay, so this means that every point in the image, every point y in the image of the map f, that is every y in f omega, y is some fx, and it is an interior point of f omega. So this means that f omega is open. So the corollary of our theorem is that if for any x in omega, the rank is m, then the image is open subset of Rm, because f maps to Rm. Okay, so this corollary is an extension, is a generalization of our previous open mapping lemma. Before we prove the inverse function theorem, we have established an open mapping lemma, which says that if the Jacobian determinant for f omega to Rn, if the Jacobian determinant is nowhere zero, not zero for all x, then the image is open in Rn. Okay, this is the open mapping theorem we prove as a parallelization for the inverse function theorem. Okay, so our corollary here is a generalization of this open mapping result, because when m equal to n, the rank is m, that is n, is precisely the determinant not zero. Okay, therefore this corollary is extension of the previous open mapping theorem, because the previous open mapping theorem applies to maps between Euclidean space of the same dimension. Well, our corollary here can apply to much wider class of map. Our map can be a map between Euclidean space of different dimensions. Okay, so this is the corollary. And but the corollary as a corollary of our theorem depends on the inverse function theorem. In our proof of the theorem, we apply the inverse function theorem, and the inverse function theorem is also depends on the previous weaker open mapping theorem. Okay, so our corollary could not be considered as a new proof of the previous open mapping theorem in this sense. However, the inverse function theorem, we can also prove the inverse function theorem without applying the previous open mapping lemma. We can have another method. Traditionally, the inverse function theorem is proved using the contract mapping principle. Okay, using the contract mapping principle, we can prove the inverse function theorem without using the previous open mapping theorem. Then, having proved the inverse function theorem, we can establish our interior point theorem. We prove at the beginning of today's lecture. Then we have this corollary, the stronger open mapping theorem. Okay, so this is the relation. These are the relations between these results we have proved recently. Okay. Now I hope that this theorem, the interior point theorem, okay, can demonstrate, can motivate you how to apply the inverse function theorem. The trick is that construct a map between Euclidean spaces of the same dimensions, because the inverse function theorem can only apply to this situation. Construct a map between Euclidean spaces of the same dimensions from our given map. Okay, so here we prove that when the linearization at the point A is surjective, then f itself is locally surjective. This is the content of our theorem, and I invite you to consider the other case. How about the case that the linearization at A is injective? So can f be locally injective? And if you are sure that it should be true, can you prove this? Okay, this is a very good exercise for you. Okay.